For decades, we've debated diets: sugar versus fat, calories versus carbs, keto versus plant-based. But beneath all those arguments lies the same quiet mechanism, the fructose pathway. It isn't triggered by sweetness, it's triggered by signals of surplus and stress. And that's what keeps the modern metabolism running in a constant state of conservation. When glucose, salt, alcohol, or stress rise beyond what cells can easily manage, the body activates a small enzyme system called the polyol pathway. This pathway converts regular glucose into fructose, flipping the same metabolic switch as dietary sugar. It's a built-in response that slows energy use and stores fuel for later, a system meant to balance abundance and protection. The problem isn't that the system exists. It's that modern life keeps it permanently active. Inside the cell, two enzyme conversions make this possible. Aldose reductase turns glucose into sorbitol. Sorbitol dehydrogenase then converts sorbitol into fructose. And once that happens, the same chemistry of fructose begins again. ATP drops, uric acid rises, and mitochondria shift into low gear. It's not about sweetness. It's a biochemical signal. There's plenty of fuel, so slow the burn and store the rest. What triggers it? High glucose. After a carb-heavy meal, blood sugar spikes, and to prevent overload, the body then diverts some of that extra glucose into the polyol pathway, converting it into fructose. An excess of glucose means an excess of fuel. And so if we don't need it right away, turning some into fructose tells the cell to slow down its burn rate to ensure more of it will be stored for later. But when meals are large and frequent, the pathway runs constantly, creating a low-level energy slowdown that just keeps building up over time. What else? Salt and dehydration. When blood becomes more concentrated, it becomes more salty, just like reducing a sauce. And the body interprets this as dehydration, which means that too much salt or not enough water is the same thing. Fructose metabolism helps conserve water by lowering energy expenditure and generating a small amount of metabolic water. That's adaptive, again, in short bursts. But with high salt diets and chronic underhydration, this water mode rarely turns off and fructose keeps getting generated. What else? Alcohol. Scientists often refer to alcohol as fructose by another name because both use similar enzymes and lead to the same endpoints: ATP depletion, uric acid elevation, fat production, oxidative stress. Alcohol also happens to worsen dehydration, stacking directly on top of the same metabolic signal. But there's more. There's stresses. Low oxygen, also known as hypoxia. Low oxygen is actually more common than we think. It's present in sleep apnea, poor circulation, or even just excess fat across the chest. All of that activates the polyol pathway because when oxygen is limited, the body shifts towards fructose metabolism as a temporary backup for energy that doesn't depend on oxygen. But in obesity, nightly oxygen dips make the liver and fat tissues steady fructose producers. One reason why weight gain becomes self-reinforcing once it begins. But there's more stresses. Psychological stress is also a factor. Stress hormones like cortisol and adrenaline raise blood sugar and alter the cell's redox balance, nudging glucose towards fructose production, which means even mental or emotional stress can sustain the same chemistry, quietly maintaining cravings, inflammation, and fatigue. And this also means that poor sleep will stack on top as well. All of this really adds up to a wide range of redundancies. Taste and preferences stack right into this. Sweet foods, salty, umami, our taste preferences are wired directly into these triggers. Sweet signals carbohydrate availability. Salty reflects hydration needs. Umami comes from purine-rich foods that raise uric acid, amplifying the same pathway. And so these cues once guided us towards survival because conditions were uncertain. But today they simply overstimulate, keeping the fructose switch on nearly all the time. Once the pathway is active, it tends to feed itself. As fat accumulates, oxygen delivery drops, and blood flow becomes less efficient, increasing hypoxia. Full glycogen stores retain large amounts of water, pulling fluid from circulation and adding to dehydration. And meanwhile, as mitochondria output slows and cellular energy drops, cells begin to resist insulin, not out of excess, but as self-protection. They can't process more glucose until energy flow recovers, so they block that signal to take it in. This creates a body that behaves as though it's both overfed and starving at the same time, surrounded by energy but unable to access it efficiently. Even without dietary sugar, the chemistry keeps running, a loop where stress makes fructose and fructose makes stress. Now, this is not about bad foods or broken biology. It's actually the opposite. It's about elegant redundancy, one system serving multiple purposes. When resources are high, it slows metabolism so that you can store more of those resources. And then when stress hits, it preserves energy to survive the strain. It's efficient and it's protective, but it assumes that the world is difficult. Modern living delivers both abundance and stress all at once. So the system never actually resets. And the result is chronic conservation, the engine always idling when it should be running in full speed. Fructose metabolism, then, is the body's universal energy management program. The same chemistry that helps us survive drought, hunger, and exhaustion. And its purpose is very simple, is to prepare for scarcity and endure hardship using a single signal. But when that signal never turns off, abundance starts to look like famine, and the body keeps storing, conserving, and craving more. In the next episode, we're going to see what happens when that chronic conservation program takes full control, how fat gain, fatigue, and cravings emerge not as accidents, but as intended outcomes of this deeply built energy-saving system.